biological, or trace metal. And we need to ensure that the presence of those doesn't skew our results in any way, and that we're still accurately reporting arsenic concentration. We also want to be sure that our device is user-friendly, so that means that it's simple, intuitive to use, and requires minimal training for any form of customer. In terms of rapid and robust, we need to make sure that our test is rapid, has a quick turnaround time, and is also robust and able to withstand those sort of adverse environments in those developing nations. We also need to be sure that our device is equipment-free, or at least in our case, as equipment-reduced as possible. We want to be sure that our device is portable, easily delivered from one place to another, and also that helps attribute to a lower cost system. So along with the Assure criteria, one other major event that's helped shape the way that we design our device is we were able to conduct an initial round of field testing just outside Calcutta, India last summer. So we were able to take proof of concept technology, just trying to prove that electrochemical detection could detect arsenic out in the field. And we were able to prove that and show that electrochemical detection detects and quantifies arsenic levels and tests those groundwater sources directly. But as you can see on the picture below, we have some trace wires going from one to the other. We have an exposed circuit board. We have a laptop, class, reagents. Just really, showing that yes, the foundational technology works, but we need to ensure that our device is much more simplified, is safe to the user, doesn't require them to be exposed to any sort of reagents or strong acids, and Ben's going to go into that later. And then just make sure that it's very compacted and portable as well. So another thing that we took to shape kind of our design constraints when designing our device is the competing technologies currently out in the field for arsenic detection in water. There's three primary methods. The first method is calorimetric testing. If you can remember, the first qualification in the Assure criteria was affordability. This first method does fulfill that. It's very cheap. It's a cheap paper test, kind of what you would see in a pH strip, which produces a color change in response to whatever concentration of arsenic. It is disposable too, but it's also horribly inaccurate. And so it's not able to detect at a very sensitive level and provide a very effective means of quantification. And so the user wouldn't be able to know the concentration of arsenic in whatever water sample they're testing. The second method is inductively coupled plasma mass spectrometry, which is more conveniently known as ICP-MS. This is the gold standard for arsenic detection and the most accurate way of doing so. It's also an immensely bulky and expensive benchtop test, so you would have to take your samples, figure out a way to refrigerate and preserve them, send them over to whatever lab had that equipment. It's expensive, it takes a long time, and so it's just really unsuitable for those sort of communities to expect for regular monitoring of their water. The third method is bulk electrode system. This is where you take 3 electrodes and put them into this glass cell and apply in the water sample after treating it with acid, and then hooking that up to an electrochemical analyzer. This is actually what we took on our first field testing trip to India. And so it's a little less expensive than the ICP-MS, but it's hazardous in that you're having the user treat the sample directly with acid. We would never want the user to come into contact with that directly. It's also not disposable, and so it has some intricate cleaning methods, and it's just the way that you have to set up the system and put it all together, it's just really not simple or suitable enough for that community. So essentially, we've come up with these 5 primary qualifications to ensure that our device is suitable for those developing regions in India and Bangladesh. The first, we want our limit of detection to be less than 10 parts per billion. That just puts us below the World Health Organization's threshold and ensuring that we're accurately reporting our results. Going along with that is selectivity, so we're ensuring that our device is selectively detecting arsenic regardless of whatever contaminants are in the water. Also, making sure to keep the user in mind, we want to avoid false negatives and false positives. This is an ethical implication. We need to make sure that we're not telling the user that the water is safe to drink when it's in fact not, and then also, contrarily, we don't want to raise any false alarms when their water is in fact safe to drink. Also, keeping the safety of the user in mind, we want minimal pre-treatment of test sample, and then to ensure affordability, we want our unit cost per strip to be less than $1.
Okay, so keeping those engineering criteria in mind, along with the Assure criteria Jessica mentioned earlier, we've come up with this integrated system for arsenic detection.